All right, so welcome back. This is part 2 of section 2.2. So in this session, we're still taking a look at evaluating limits, but what we're going to evaluate limits numerically now. Instead of using a picture, a graph, we're going to take a look at a numeric approach to evaluating that limit. All right, so what I have here is I have a function, and I want to find the limit. Now, as you can see, I'm taking the limit as x approaches 0. If you were to attempt to use direct substitution, you would get 0 divided by the square root of 0 plus 1 minus 1, which is 0 divided by 0. And what does that tell me? It tells me that there is a hole in the graph. And that's a good thing to know. That's a bad thing because it's not evaluatable there. But it's a good thing because if there's a hole in the graph, that means it looks like this. And if there's a hole in the graph, that means that the left side and the right side are going to approach the same value. So although it makes it more work, I like when I see 0 divided by 0 because it tells me what to do. It gives me a way to make this work. All right, so you'll notice I have the calculator up because I'm going to use my calculator to do this. The first thing I need to do, though, is I need to take the function that I'm finding the limit of and put it into the calculator. So I'm going to go to my y editor and I'm going to put that function in. So let's see, my numerator is x, my denominator is the square root of x plus 1 minus 1. Okay, that looks good. And then I'm going to go to my table. Oh, and it looks like my table is set to automatically or autofill x value, so I want to change that. So where it says table set right there above the window key, I'm going to go to my table set. I'm going to change my independent variable to ask. And what that does is it says, hey calculator, make a table, but ask me or let me input the x values that I want to use. Okay, now I can press enter all I want, nothing's going to change. Oops. I can press enter all I want, nothing to change. I just need to go back to the table and then I'll see the change. Now you notice that there's nothing there. Now at this point, what I'm going to do is I'm going to input the x values for the left-hand limit, from the left side, and see what happens there. Now, why were those numbers chosen? Well, those are numbers that are close to 0, but to the left of it on the number line. So negative 0.01, negative 0.001, and negative 0.0001. And so what I get for my y values there are, I get I don't want the highlighter, I want the pen. 1.995, 1.9995, and 1.9999. Now, do you see a pattern in those numbers? Do they appear to be approaching something? Right? And if you don't see a pattern in those numbers, or you don't see it approaching something, add some more columns to your table and put some more values in. Now, I'm fairly certain that this looks like from that left side over there that this is getting closer and closer to 2. But I'm not done yet, because for a limit to exist, both sides have to approach that same value. So now what I'm going to do is I'm going to go over there and try those other numbers, those positive ones. So 0.01, 0.001, 0.0001. And it looks like this was 2.005. And this is 2.0005. Now that third one looks like 2, but if I actually scroll over to it, you'll see down at the bottom, it's actually 2.00005. The reason the display only shows 2 is because it's limited to, what is that limited to? 4, 5, 6 digits, a decimal place in 5 digits, before it has to just round. It looks to me like from the right, this is approaching 2. So from that left-hand side, numbers smaller than 0, it's getting close to 2. Numbers larger than 0, it's getting close to 2. So I am going to say that I think, numerically, that this has a limit of 2. So my numerical example, I think that this has a limit of 2. Okay? So this is a numerical evaluation of a limit. I pick values to the left on the number line of my, and in terms of limit language, that's called C. That is the value where you're taking the limit. You take the limit at C. So I pick values to the left of C on the number line. That's what these guys were. I pick values to the right of C on the number line. That's what those guys are. I evaluate the function and find those y values, those functional values. I look for a pattern in those functional values and ask myself, is it approaching a number? Is it approaching something? So coming in with those numbers to the left of 0, it looks like it's approaching 2. And then going in with those numbers to the right of 0, it again looks like it's approaching 2. So it looks like both sides come together at 2. And then to write it all out correctly, in the end, I would say this, that the limit as x approaches 0 of x divided by the square root of x plus 1 minus 1 is 2. Now you'll notice that I didn't just call this f of x, and the reason I didn't call that f of x is there is no anywhere in this problem where that is defined as f of x. It just said find that limit. I can't just toss an f of x into my answer if f of x was never defined anywhere. Okay? All right, let's take a look at another one. Evaluate the limit numerically. Now, if I try to just use direct substitution and toss in the 2 and see what happens, when I try to do direct substitution, I get 4 minus 3 times 2, 6 plus 2 divided by 2 minus 2. That's 0 over 0. And so what does 0 over 0 mean? Someone punched a hole in my graph. I like holes in my graph because that means that even though it's not going to be easy, the left side and the right side are going to come together, most likely, and I will get a limit. Right? How did I know to plug in 2? Oh yeah, the limit told me to use 2. Now I've got the table set up for me. You'll see that we're going to use 1.9, 1.99, 1.999 for numbers to the left of 2 on the number line. We'll be using 2.1, 2.01, and 2.001 for numbers to the right of 2 on the number line. But the first thing I have to do is I have to put this function into my calculator so that I can evaluate that limit. So I'm going to come back over here and clear out that one. I'm going to put that new fraction in there. I have x squared minus 3x plus 2. That's my numerator. My denominator is x minus 2. I'm going to go back to my table. I've got all these old x's in there, so what I'm going to do is I'm just going to delete them all out. And now I'm going to use those numbers that I highlighted in yellow over there, the numbers that are to the left of 2. So 1.9, 1.99, 1.999. And so what do I get? I get 0.9, 0.99, 0.999. Okay? Do you see a pattern? Does it appear to be approaching something? If you can answer that question, then answer it. If you can't, use some more numbers. See if you can see a pattern then. Because it looks to me like it's approaching 1. Right? Now I'm going to check to the right. So I'm going to use those numbers that I highlighted in pink. 2.1, 2.01, 2.001, and see what happens. So this was 1.1, this is 1.01, this is 1.001. So I'm seeing, and I hope you're seeing the same thing, that coming in this way, it looks like it's approaching 1 again. So if the left side is approaching 1 and the right side is approaching 1, what are we going to say the value of the limit is? We're going to say the limit has a value of 1. And then so to properly write it aloud in the end, we would say that the limit as x approaches 2 of x squared minus 3x plus 2 divided by x minus 2 is 1. Numerical evaluation of a limit. I'm using my calculator because this is the easiest tool I have to do this. I'm using the table function not because I have to, but because it makes it easy. I could just be evaluating each of these in the home screen, and that would be fine too. All right. Conceptual question. We said a moment ago there's a hole in the graph. What are the coordinates of the hole? Like if this was on a set of axes, what are the coordinates of that hole? What's the x value and what's the y value? Okay. Well, what's the value of the limit? The value of the limit is when x is 2, y is 1, or more precisely I should say, the value of the limit is as x approaches 2, y approaches 1, which is what gives us the hole in the graph and the limit of 2, 1. Right? Sometimes, though, limits won't exist. We've taken a look at a couple examples where limits do exist. So what would it look like if we had one where the limit didn't exist? Right? So I've got a new function, and I'm going to approach the limit as x approaches 0. So I am finding the limit of the absolute value of x divided by x as x approaches 0. And I'm wondering what that value is going to be. Okay? So again, back over to my calculator. First thing I have to do is put that function. So back to my y editor, make that one go away. I'll put another fraction in there, and then in my numerator, I'm going to put in the absolute value of x divided by x. Enter. Back to my table. I need to get rid of those values, so I'm just going to delete them all out. Okay. And now I'm going to check the numbers that are to the left of 0. So negative 0.01, negative 0.001, negative 0.0001. I wonder if it's doing the same thing it was doing earlier, where it's just rounding. No, it looks like these values are all negative 1, negative 1, negative 1. So what is it approaching from the left? It appears to be approaching negative 1. And now what I'll do, I'll check those values from the right. Oh, it looks like I made a mistake there. That should be negative 0.0001. Oh, luckily it doesn't change anything. I'll check the values from the right. So 0.01, 0.001, 0.0001. This is 1, this is 1, this is 1. So coming in from the right-hand side, what does it appear to be approaching? They're all 1, so it looks like it's approaching 1. So what does that mean? If the left side's negative 1, the right side's positive 1, they're not coming together at the same number. These aren't the same value. And if those aren't the same value, then our limit does not exist. I don't trust myself. I want to take a look at a graph. So I'm going to go back over here, back over to Desmos, close that, get rid of that, get rid of that, get rid of that, and I'm going to graph that function. So we were told its name was f of x, and it was equal to the absolute value of x divided by x. And if I look at the picture, the graph of this thing, it looks like two horizontal rays that both come together and stop right there on the y-axis. Yeah. Well, that makes sense then. that makes sense that the limit doesn't exist because the left side's down there a -1, the right side's up there a +1. So if I go back over here and I copy that down, make a quick sketch of that thing. This side was here. This side was here. This was +1. This was -1. The graph is not evaluatable at 0 because if I try to find f of 0, I get the absolute value of 0 over 0. Okay? So there's a hole in the graph. The problem is this isn't a good hole. This is a bad hole because the left side and the right side don't match up. So this is an example of where 0 divided by 0, usually that's a good thing, but here's a great example where direct substitution gives you a bad thing. So this limit fails to exist. It fails to exist because the left-hand limit and the right-hand limit don't match up. The left side and the right side. Okay, there are some common types of behavior associated with non-existence. The first one is the one we just looked at. The function approaches a different number from the right side of C that approaches from the left side of C. Another way for a function to not exist would be to have a function that increases or decreases without bound as x approaches C. What does that mean? Well, I'm going to steal these axes right here and take a look at what that means. And I'm going to do a very uncomplicated example. Suppose that we were given the function, why did that do that? Suppose that we were given the function f of x is equal to 1 over x. About as uncomplicated as you can get. And suppose that someone wanted us to find the limit of that function f of x as x approaches 0. What is that limit going to be? Right? Now, if I were to make a graph of that, and I remember from my college algebra what the graph of that looks like. The graph looks like this. Right? And so if I attempt to evaluate this graphically, well, on the left, as I get closer, the graph goes down and down and down and down. It increases without bound, or it decreases without bound. In this case, we would say that it decreases without bound. Right? Decreases without bound just simply means it's going down towards negative infinity. So you might remember that from your college algebra class. I mean, you probably should remember that, say it like that. You should remember from your college algebra class. Okay? Remember what was the name that we gave to this right here? That was our vertical asymptote. Okay? And so we have something where from the right it increases without bound. From that left-hand side it's decreasing without bound. And so we would say that then, since the two sides don't come together, this limit does not exist. Right? Now the last one's kind of a tricky one. F of x oscillates between two fixed values as x approaches C. So rather than give you a function for this, because the functions that do this are kind of ugly to look at, we'll just make a quick sketch. What if we had a graph that did something like this, that wiggled, but as it gets closer and closer to 0, it wiggles faster and faster, and then as we move away, it wiggles slower and slower. And imagine I could draw better. And that in here, and we were trying to take the limit, and I'm going to call this thing g of x just because I got to give it a name. So that's g of x as x approaches 0. And if we look there, if I try to trace it with my fingers, it wiggles so much in there that I can't see where it's going. It's not approaching a fixed value. And because it doesn't approach a fixed value, it doesn't have a limit L. And so we would say this does not exist. Now, I will tell you that of these three, 1 and 2 are the ones that we run into most often. It is rare to run into number 3. You really have to work hard to come up with an equation that does that, whereas the other two are fairly common. It is fairly common to have left side and right side not match up, or to have something that has a vertical asymptote where it increases or decreases without bound. Now, one thing I want to make clear, I didn't quite make it probably as clear as it could have been. My example for number 2 had one side going down and one side going up. If you had a graph where both sides went up, or if you had a graph where both sides went down at a vertical asymptote, you would still say that that limit does not exist. That's just the way we define it. Okay? Because yes, they're both going in the same direction. In a sense, they're both going to infinity. But the definition for a limit requires that we approach a number, and infinity isn't a number, it's a concept or an idea. Right? All right, the last little bit here is the formal definition of the limit. I know we're a little bit over 20 minutes, and I try to keep them short, but we're just going to take a look at this here. It is not something I'm going to be testing you on. You probably won't see it again until you get to a higher level calculus course. What I mean by that is like a 300 or 400 level calculus course. But the formal definition of a limit says this, that you have a limit of L if for any little interval around L, that is, for any little interval around L, you can find an interval around C that'll stay inside of that. So if I told you that the limit of some function f of x as x approaches 2 is 5, then what you could say is, okay, make that epsilon be 0.1. So then this number up here would be 5.1. This number down here would be 4.9. And this number right here would be 5. Right? This number would be 2. And then I should be able to find a value for delta. And I don't know what it is. I'm just going to make it up. Where staying between C plus delta and C minus delta will keep me between 4.9 and 5.1 on that y-axis. And maybe 0.1 isn't accurate enough for you. Maybe you want 0.01. And you want to be between 5.01 and 4.99. Well, if the limit really is 5, then I still should be able to find a delta that makes that happen. Oh, maybe 0.01 isn't accurate enough for you, and you want 0.00001. So then I should be able to find a value, 5.00001, right? 4 zeros, yeah, and 4.9999. That means I should be able to find a value for delta, that if I stay between 2 plus delta and 2 minus delta on that function, I will be closer to 5 than 0.0001. This is the delta epsilon, or the epsilon delta, depending on who wrote the book, approach to this. And basically what they're saying here is they're saying that there exist numbers out there for these. Tell me how close you want to be to the limit. Tell me how close you want to be, and I will be able to find an interval around C to make that happen. That's the formal definition of a limit. And so if you take a 3 or 4 or 500 level analysis course, which is where they study calculus more rigorously, you will prove this to be true, and then you will find values. Someone will say, hey, here's epsilon, find me delta. And your job will be to make that happen. Okay? So this is the formal definition. Again, I won't be testing you on it, but I wanted to make sure you've seen it in case it comes up. All right, this brings us to the end of section 2.2. So at this point in time, you should be able to find the value of a limit numerically or graphically or both. Okay? So numerically or graphically or both. All right, see you back here for 2.3.